Hello and welcome back. So we keep visiting more turbulence models in OpenFOAM. In our benchmark case, the flat plate. So now we move to the K-Epsilon family now. So we already covered K omega and spiral matters. So hopefully we're getting a better idea how to set up turbulence simulations in OpenFOAM. Now we're discussing how to set up boundary conditions at the wall, choosing the combinations, and also how to validate the case, how to know if whatever you're doing, it is correct. Okay, so before moving to the K-Epsilon family, I would like to address a little bit some theory. So basically in the deck of slides we cover this, and you will find this table, how to the different combinations of the different boundary conditions now at the wall, according to the treatment wall modeling and wall resolving. So this is important, get familiar with this. So now we're going to focus in the K and epsilon variables. So as a guideline here, if you are doing high-ray wall modeling, epsilon at the wall should be the epsilon, that the free stream value. Then at the wall, recommended value 0, but we're going to we're going to study a little bit to why that value and the different combinations that you have here of epsilon. Also in this table, I mentioned that you can put fixed value, those boundary conditions. That is not recommended. That will be disabling everything. There is no blending functions, damping functions, no behavior. So that will be, let's say, probably it's not the proper term, but it will be a DNS, or you are trying to resolve everything, okay? So it's not correct. So here I put not recommended. So that being said, also, let me remind you as well, we cover this definition of Y plus and Y star. So Y star, this is the definition used. So when you use the nut K boundary condition in OpenFOAM, this is what you are using. And here you have the reference. So this is something specifically developed for the K-Epsilon, for wall modeling, has been extended also to deal with wall resolving. So later we're going to study that a little bit, but just to mention that you have this formulation. Also in this formulation, the production terms, it changes a little bit, not to take into account this behavior, but to stress that this formulation originally is just wall modeling, as I say. And the standard version that we have of Y plus is this one, or the one that we know. But the problem is that if you have separation reattachment, this might become 0, and that can create a singularity, which is not a big deal. You have there an iterative method close to the wall. You have some value to avoid division by 0 and so on. But in any case, I bet it is an improvement. And then what you can do, so here I'm using the U star, but it's U plus as well. So this is, we can call kind of the scalable approach, that you subdivide when you are solving boundary layer, you compute Y plus and you subdivide your loop, whatever you're doing. And then if your Y plus is less than a given value, use this approach. That is, if you are in the viscous layer, use this approach. If you are in the low layer, use this approach, and usually that value that tells you what approach to use is related to the intersection between these two. Okay, so usually this intersection is 11 something, depends in the constant that you use. But according to this intersection, you say, okay, if your value is more than this, use this, the log law, and it's less than this, this. And then also you have the blending. Okay, so there are different approaches. So we talk about the Spalding law that will do a small blending. Then you have the Kader function, the green one that you see. So this transition layer, the buffer layer, is very energetic. There is no universal law, so that's why we try to avoid putting the first node there. Okay, but nevertheless, there are a few approaches that try to improve or to reduce the errors that you will find there. Okay, so I just visited that, and before moving to the K-Epsilon model next video, I would like to revisit the logic behind our turbulence models. Also, let me show you here that you have in the training material in the lectures now, you will find this lecture now, and here you have the derivation of the RANS equation, the steps. So here you have pretty much from the incompressible, the assumptions that you take. We talk about some averaging rules here. You have these rules, and then the steps you follow, and doing that substitution, you get your RANS equations. And then you have the business approximation, okay? Then also talk from where this term is coming, so it's something mathematical, okay? So here you have everything in the description, and that's it. So if you are in doubt, just read this small document. I guess I need to expand it to add now the solvable equation that basically you introduce your business approximation into your RANS equations. You get the solvable, and that's it, okay? Then you solve your problem and take your approach, what model, what resolvents, and everything, different models. Okay, that being said, let me start here. So we know that we have the general equations, we add models to that, then we talk about RANS, but also we have less models, and the derivation is pretty much the similar node that you will find in those nodes. And at the end of the day, just reducing the problem to the incompressible case, but it doesn't change that you go compressible. Okay, there are a few new considerations, but pretty much the same. So everything now is expressed in terms of the average variables, and then you have this new term that is the Reynolds stress, is what we want to model using the business hypothesis, or you can use the Reynolds stress models that we're going to also visit. Okay, so Reynolds stress doesn't use the business hypothesis, it solves all the Reynolds stresses. So mathematically speaking, let's say it would be the best model, but personal experience is difficult to get converged, okay? But let's move here. So your starting equation. So what I mentioned that we add in the business hypothesis, the eddy viscosity models, okay, we approximate this here using the business approximation, then we introduce that in the RANS equation, and we get this set of equations. These are the solvable equations, and now our task is to approximate to get a value for mu t. Also, in this set of equations, if you don't compute k, that can be a problem, or not a problem, but just neglect this, or you can approximate it using algebraic models. So we talk a little bit about this when this parallel matters that doesn't compute k. But now let's look at the logic. And to look at the logic behind a turbulence model, okay, let's talk about the standard K-Epsilon model. So here, as usual, I always give references. You need to know the references, okay, of each turbulence model. So this is the very standard one, the one proposed by Launder and Spalding. This is the first reference. So basically, these are the equations. These are the solvable equations. And here, look at that. We already introduced all the coefficients or constants now. So they have been properly calibrated, okay? So all the physics, it is contained there. And I guess I need to talk a little bit these coefficients in another video. It's very interesting now because, yeah, you have all your physics there. So basically, this is what we're going to solve by transporting this equation that takes the form. We also look at that as a general transport equation, but it's not like that. It's not as trivial as that, no, because there is a formal derivation for K and Epsilon, okay? And then after taking some assumptions, we get to this, okay? But it's not like, let me take the general transport equation, let me put up production and dissipation, and then diffusion term, no? Transportation term. Okay, it's not as simple as that. So at the end of the day, in this turbulence model, we compute the turbulent viscosity like this, okay? This is solely based in dimensional analysis, okay? So you look at the units of these two quantities, you get the viscosity or kinematic viscosity units. Usually, just doing this dimensional analysis, you add constants. So I could call this A, but it puts mu that we're already familiar. Okay, but later we're going to talk about this mu that is very important. You will see it all over the place in turbulence model. So talking about units here, just to remind you the units K, Epsilon, viscosity, and so on. So as you go back here, do your dimensional analysis, you will see that combining this, you get this unit. So turbulent viscosity has the same units as molecular viscosity, okay? That is just dimensional analysis, okay? So let's study the logic behind this model or any model. So entirely based on dimensional arguments, we can say that molecular viscosity and turbulent viscosity can be expressed as a combination of a velocity scale and a length scale, okay, entirely based on dimensional arguments. So Reynolds stresses, we have seen that is correlated to the velocity fluctuation. So it makes sense to use the turbulent kinetic energy as a velocity scales. Okay, turbulent kinetic energy will relate it to those fluctuations. So let's say that the velocity scale is something equivalent proportional to the square root of turbulent kinetic energy, where K is this. Okay, remember, these are your velocity fluctuations. This is what you want to model. And then let's talk about epsilon, which is the dissipation. Okay, dissipation of what? Of this turbulent kinetic energy. So basically, we're dissipating turbulent kinetic energy per unit time. Okay, and it can be expressed as follows. Okay, so look at that. Now we introduce L0. Okay, so we need to have another variable to compute this dissipation. L0 are the integral length scales. Okay, so based on that, we can say that L0, okay, is equivalent to this, just dimensional analysis. Then also you can compute at eddy turnover time like this, entirely based on dimensional analysis. And kind of just to clarify this, that L0 represents, let's say, the approximate distance where all eddies move during all the events contributing to turbulent transport. Okay, it does not represent L0, the diameter dimension. It's just a region where you're going to have all these events contributing to the turbulence transport. Okay, it can be from small to large scales. You will have everything there. So basically, using these definitions, then dimensional analysis, and we can get that turbulent viscosity, it is proportional to this, and usually just multiply this by a constant, and that's it. Then your task, okay, is to get the value of that constant. Something interesting just to mention here regarding epsilon also. Epsilon, or the units that we have in epsilon, we have this unit because we're dissipating what? K per unit time. Okay, so that's why we get those units. So just dimensional analysis, common sense. Okay, so let me go here. So in this model, we use this scale. So for velocity, L0, then we compute the viscosity like this. And important to mention, not to say that this is called, these models, 2 equations, 3, 4, 5, 6 equation models are called complete models because from the combination of variables, you can get integral length scales, or you can define other variables. Instead, 1 equation models are called incomplete because you cannot get that. So that is the case of these parallel matters. However, using good engineering, judgment, you can formulate those models by calibrating properly all your variables. So that's it. And what I mentioned, that K and epsilon, they are not general transport equations that we throw in and just try to get the equations, the coefficients there. There is a proper derivation. And for instance, this is the exact K equation, turbulent kinetic energy. So see that when we look at the exact, we can look at the budget of this equation, the contribution of each term, that you have a brief description here. Also, I didn't put here the reference of the paper, but it's like for the 40s, 1940, the paper, the first derivation. So basically, starting from this equation, then we can get the solvable. So we take approximations. We say that this term can be approximated like this. We add constant, this triple correlation that you can see is very complex, how we can approximate this, and you say all this corresponds to the diffusion and transport of fluctuations. So usually all that stuff, if we look at the model equations, basically we dump everything here in this term. Then you have dissipation and production. But there are some assumptions taken there, and during those assumptions, the coefficients derive and so on. Okay, so there is a logic. And the same is for the dissipation equation. This is a little bit more complex. Okay, actually it's a very complex equation, and many of the problems of this K-Epsilon problem is how to give an actual interpretation, how to approximate this equation, and what assumptions do we take. So here you have each term, what kind of, we can say, represents. Here I put the references from where, how to derive. And the derivation can be dated back to 61. Okay, so there is a lot of mathematics. It's not a so difficult exercise, but there is a lot of mathematics, algebra to derive this. And from this, basically take the right assumptions, and you're going to get this equation. So this is the logic behind turbulence model. So also, when we talk about the budget, see that in each of these equations, you will have different contributions. So we have here the budget for the turbulence kinetic energy and the budget of the dissipation rate. So each term that appears here, you can easily see here the contributions. Well, what we were talking that when it comes to turbulence kinetic energy, production peaks in the buffer layer that you can see here. You see how everything balanced. So when things are in equilibrium, production equal to dissipation, but then you have all the contributions. Look at that, these terms will redistribute everything in your boundary layer. So it will redistribute something towards the boundary layer, but also away from the boundary layer, and so on. And in that case, you will have epsilon always acting, dissipating that, because we need to have a viscous so layer which is laminar. And something similar now we can say about the dissipation, a little bit more complex, how you have all this interaction, but yeah, these are our budgets. So just to end, just to revisit this table. So we go to RANS, and you can see that the mathematics behind RANS, it can be very complex, and as you go down in this direction, the mathematics is less complex. There is no modeling, no assumptions, so everything depends on computational resources. Okay, so here the computational cost is much higher. Okay, so this is the logic behind turbulence models. I hope you have now a better idea. Similar logic can be applied for the omega and so on. Okay, so in the next video we're going to visit the K-Epsilon, each of the single variations that we have. So thank you for your attention, and see you next time. Bye.